No, I like that. I love it.
Okay.
Like what for you?
All right, everybody's attention, please. We don't have much time. So here we go. We have quick review from yesterday, really quick review, because we have a lot of stuff to talk about. If we had point C, which was -3,2, and point D, which was 5,8, and we wanted the coordinates of vector CD, what would the coordinates of vector CD be? Pete, why is absolutely nobody back there paying attention to me?
Because I got really distracted talking about
Who said that?
Okay, what's the word person in real life right now?
I'm still a little upset you turned me in, so you know it's kind of like my act of defiance.
Just doing my job. Okay,
I was trying to do mine.
from C to D, how would we move if we started at C and went to D? What do we do? -3 to 5 would be 8, and 2 to 8 would be 6. Those are called the coordinates of that vector. These are called the vector coordinates of the directed distance. Now, there are other ways to express that. So I want to talk a little bit about a couple of really special vectors. They're so special they have their own names. They're called I and J. The vector I is what we call the horizontal unit vector. In other words, if you drew a picture of it, its coordinates are 1, 0, so it would just go over 1 and up 0. It is the horizontal unit vector. What do you think it means to be a unit vector? Its length is 1. So the horizontal unit vector is called I. It's 1, 0. And then J is the the vertical unit vector. So it looks like this. So this is I and this is J. Sometimes vectors, instead of being written as in the coordinate form or the component form, sometimes vectors are written in terms of I and J. So another way of expressing vector CD would be 8 I's plus 6 J's. Now do not be confused by that. Remember, what does I represent? I represents 1 horizontal step. So if this guy has an x coordinate of 8, wouldn't that be 8 horizontal steps? So that's 8 I's. And then similarly, this 6 would represent 6 vertical steps. So any vector can be written in terms of I and J by taking that, whatever the x is times I and whatever the y is times J. This would be called a linear combination of I and J. So a question might read, write -3, 2 as a linear combination of I and J. That is easy. It takes forever to write the problem. It sounds really complicated, but it is easy. What would this vector be in terms of I and J? -3I plus 2J. Just remember, it's an addition. It's not a comma. It's an addition. That's it. Easy. Now, let's go back to our vector CD here for a minute. You found the coordinates here of this vector. Let's suppose we wanted to know the magnitude and direction of that vector. So find the magnitude and direction of that vector. Now, it's important to keep in mind that vectors are directed line segments. So they have direction and they have magnitude. Magnitude is the word for length. So they have direction and they have magnitude. They have direction and they have length. Every vector has those things. Every vector. So you're finding it for this particular one. Now, one of the nice things about vectors is they can be drawn anywhere you want to draw them. This vector, the only restriction is getting from start to finish, it has to go right 8 and up 6. So the easiest way for me to draw that vector is like this. Over 8, up 6. Just start at the origin and go over 8 and up 6. That is a picture of vector CD. Now, I don't have to start it at C and stop it at D. I certainly can. I'm allowed to start it anywhere I want as long as I move this way. I want to know then, if that's vector CD, the vector that goes right 8 and up 6, I want to know this angle, because that will give me the direction of the vector, and I want to know this length. Well, do you have an idea about either one of those? I could use second tangent. I could say the tangent, let me call it theta. The tangent of theta equals 6 over 8. So theta is the angle whose tangent is 6/8. That would be called the direction angle for the vector. It's in standard position like every other angle you ever draw. So second tangent 6/8. The direction angle is 36.9 degrees. Does anybody match that? Okay, that's the direction. Now, you do want to be careful, because if the vector had been drawn over here, if it had moved this way, this is the direction angle, consistent with everything we've always done, right? Measure from the positive x-axis. So if you did second tangent and you got this to be 36, the actual direction angle would be 144, right? Okay, what about the magnitude? What about the length of this vector?
Could you do Pythagorean theorem?
Absolutely, you could do the Pythagorean theorem. Absolutely. So the Pythagorean theorem, I think that works out to 10, doesn't it?
Yeah.
So the magnitude, remember we were finding the magnitude and direction. The magnitude is 10 and the direction is 36.9 degrees. Easy. Let's try another one like that. That's a pretty important skill, so let's make sure we got that down. Let's say vector V has coordinates -2, -3. Let's find the direction angle and the magnitude. Anybody remember from yesterday what the symbol for magnitude is? Absolute value. So instead of writing the word magnitude, I might just say this. That means magnitude. Okay, so let's draw a picture of this vector. This is the vector -2, -3, which simply means from start to finish, it goes left 2 and down 3. So I might as well start it at the origin. That's the easiest place to start it from. So here it is. Here's the vector right here. Now I need its direction angle and I need its magnitude. Okay, so can you do either one of those things? I hear calculator buttons being pressed. What's being pressed? Second tangent 3/2. So second tangent 3/2 gives me 56.3. Please do not say 56.3 is the answer though, right? Because we need our angle in standard position. So the actual angle would be 236.3. Are you okay with that? How about magnitude? The square root of 13. 9 plus 4. 4 plus 9. Square root of 13. Okay? All right. Let's suppose the question said this. Find a unit vector. That means magnitude is 1. Find a unit vector in the same direction as 3, 4. So we've got a vector out there. Brian Harvey. Ben Harvey.
See, now you can't yell.
Oh, I'm going to yell at you. All right. We got a vector, 3, 4. So we can draw a picture of that. Always helps me to visualize it anyway. So 3, 4 would look like this. Over 3 up 4. What's the magnitude of that vector? 5. So the magnitude of vector V is 5. My job is to find a unit vector, and I've reminded you up above there, to be a unit vector means your magnitude is 1. You want to find a unit vector in the same direction as that one. In other words, we want to find the coordinates of this vector right here, that little blue guy. Because he would be in the same direction, but only 1 unit long. Anybody have an idea how to do that? You think about geometry, I think you can do that. What kind of proportion? You're right on track. If we looked at our little blue guy here, and some of you might not be able to see that blue marker, it's not very good, but if we looked at this little blue vector, he has to move exactly the same way this one does, except that can only be 1. Now, what was it in the beginning? It was 5, right? So we took 1/5 of it. So we're going to have to take 1/5 of each of the other sides. So instead of being 3, this little piece is going to be 3/5. And this one will be 4/5. So your unit vector is the vector 3/5, comma, 4/5. Now, how did we do that? You know, we got these juniors absent today. They're going to need to know how to do this. How can we summarize that? If we want to find a unit vector in the same direction as a given vector, we just do what? We take these coordinates and divide them by what? By the magnitude of the vector. So, let's come over here to this vector. You found its magnitude was root 13. What would be the unit vector in the same direction? The unit vector in the same direction as this one would be -2 over root 13 and -3 over root 13. Now I know that's not rationalized, but I want to leave it that way so you can see what I did. How do we find a unit vector? Divide by the magnitude. Keep the negatives, because you got to have the same direction, but divide by the magnitude. All right, now I'm going to ramp it up one little bit. Let's suppose we wanted to find a vector of magnitude 6 in the same direction as -1, 3. Anybody have an idea? I'll give you a hint. You start by doing this. What is this? What did I do here? I made the length 1. All right, so what is the length of this given vector? I should have given it a name. What's the length of that given vector? No, the given one.
6.
This one. What's the length of that one?
6.
The length of that's not 6. Oh, you guys, visualize it, visualize it. -1, 3. What's the magnitude of that vector?
Magnitude?
Square root of 10.
Oh, we're trying to find 6.
Okay, yeah, so first find the magnitude of the given vector, which is root 10. Now, does everybody get root 10? That's huge. You gotta be able to get that the length of that vector is root 10. Now, we want to make that a unit vector. Okay, so what would the unit vector be? We just talked about that. The unit vector would be -1 over root 10 and 3 over root 10.
You have to bring up the...
Now, how long is this? It's a unit vector, so how long is it? 1. This is 1 unit long. Now, how long do I want it to be?
6.
How could I take something 1 unit long and make it 6 units long? Times it by 6. So the magnitude 6 vector will be -6 over root 10, 18 over root 10. You do not have to rationalize that if you don't want to. You can find a vector of any magnitude by simply taking whatever the given vector is, making it a unit vector, and then multiplying by whatever length you want. Okay, so let's say that again. If you want to change the length of your vector, basically that's what you're doing. If you want to change the length of your vector, make it a unit vector, and then multiply it by whatever magnitude you want it to have. So if you need it for some reason, you need it to be 10, then you multiply by 10. If you need it to be 17, you multiply by 17. Here we needed it to be 6. All right, let's look. This is so exciting, some of you look so bored. Let's look on page 512 at number 44. This is what we use vectors for. This is why we have them. So we're on page 512. We're looking at problem number 44. An airplane is flying on a heading of 170 degrees. Okay, now wait a minute. Wait a minute. Everybody's on page 512, looking at number 44. And we have an airplane flying on a heading of 170 degrees. Now be careful, this is a compass heading. So do you remember 170 degrees would look like this, right? You okay with that? And its velocity, it's 460 miles an hour. So I'm going to say the magnitude of that vector is 460. So its angle, here's its angle, and there's its magnitude. Now, before we do the wind, which is going to be a separate vector, I want to concentrate on the airplane and find his coordinates. You have been given a magnitude and an angle. I want you to come up with the x comma y, the components, the vector coordinates, the directed distance for that vector. Now, I probably made it sound hard. It's really easy. if we make a right triangle here, this is x and this is y. Do you think you can find x and y? Absolutely, using right triangle trigonometry, right? First, though, we need to figure out this angle right here in the this whole thing's 170, but we need the one in the triangle. So what would that angle be?
80.
80? You okay with that? So if we want to find the x coordinate, we could say cosine 80 equals x over 460. Does that make sense to you? So x will equal 460 cosine 80. I got for x, I got 79.88. I typed that into my calculator. Everybody understand why I use cosine? Adjacent. And then sine 80. I got 453.01, but I got a caution for you. That 453 is actually negative. Why is that 453 negative?
Y is negative.
Y is negative. I'm in quadrant 4. Here are the components for the airplane. Over 79, down 453. Now, can you do the same thing right now for the wind? They give you the component, or the magnitude direction of the wind. Bearing is 200 for the wind, so that's going to be over here. Here's my wind. And the magnitude of the wind is 80. Can you find the x and the y for the wind? Before you even do it, can you tell they're both going to be negative?
Yeah.
How do I know that?
3.
I'm in quadrant 3, yep. So what will I need to do to find the x and y coordinate there? What will I need to do? Figure out this little angle right here. What will that be? Remember, this is 200. So this will be 70. So what will my equation be for x and y? 2 equations, one for x, one for y. Cosine 70 equals x over 80, and sine 70 equals y over 80. So what do we get for the width? 27.36, now that's negative, remember, for x. And 75.18 for y, negative. Now, what was the question? Find the actual ground speed and direction of the airplane. In other words, find out what happens when you add these two vectors together. What impact does the wind end up having on the airplane? Was it to push him off course and it's going to change his speed? I need to add these two vectors together and find out what happens. How do I add two vectors together? We talked about that yesterday. add the x's and add the y's. So the resultant, the addition, the sum, the resultant of these two vectors is going to be these two added together. So I got 52.52 and negative 528.19. Did I do that right? So the new vector I got, the resultant, comes over 52 and down 528. Now guess what we need to do? We need to find its magnitude and we need to find its direction. So we started with a magnitude and a direction, a couple of them. We changed them into the component form, added them together, and now we're going to change them back into their component form. So how do we find the magnitude? Oh, I feel like I'm talking to myself. 530. I got 79, but yeah, close enough. Who knows how we rounded? What does that number represent? What does 530.79 represent? The actual magnitude of the airplane. So he has speeded up. The wind is pushing him along. He has speeded up a little bit. He's going a little bit faster than he was originally. Now, what about his direction? Can we find this angle right here? How would we find that angle? Second tangent. Very good. You guys are on it. Those of you that are awake. I got 84.32. So what is his actual direction? Remember, his intention was to fly on a course of 170. What course is he actually flying on? 174.32. So he's been pushed off course a little bit, and he's flying faster than he had intended.
How did you get 174?
I did second tangent here, got 84, and then I did 90.
Oh.
Remember, I got a measure from July.
Right now.
Okay, so, sleepy people, how do we find the direction and speed of a resultant course? What do we have to do? We have to take whatever the original vectors are and recreate them in their component form. And how do we do that? By drawing a picture and doing sines and cosines, right? Once you get the component forms, then you can add them together, resultant, find the resultant. And then, once you have the components of the resultant, you can draw a picture and work backwards and get the new magnitude, the new velocity, and the new direction. Did you check my cheat sheet, make sure we covered everything? We did. So, tonight's homework, rather extensive assignment. So will tomorrow's be. All, do as much as you can tonight. All of this will be due next Tuesday. So we have a big assignment in 6-1, we have a big assignment in 6-2, and then on Monday we're going to kind of recap everything, and it will be due on Tuesday. Everyone got it? if you wait till Monday night to do these two assignments, kids, they're huge, they're pretty big. So don't do that, do a little bit today, as much as you can today, and do the rest tomorrow. Okay, all right, that's it, all right. Would you turn that on, Preston? I don't have any idea how much time we have left, but you can use this time to go ahead and